So this is the written homework session for week 8. It's all about energy, work, kinetic energy, potential energy, and its different forms, gravitational, um, elastic potential energy, all that. So for this session, we have 4 written homework problems. Normally, I would go over some of the online, but like I said, I feel like the online, um, there's some good, for sure, problems like that are math based, but in general, I just feel like it's a very math heavy kind of topic, and so the written should be sufficient to build on a lot of the understanding and the concepts. But for sure, if you guys have any questions about the written or the online, just please let me know, and I'll be happy to answer any questions about the online as well. Um, Usually, I try to get back as quick as I can, but just if I don't get back to you, just please remind me, and I'll try my best to answer as fast as I can with as much detail as I can. But yeah, so without further ado, we can start on problem 1 here. So we have work required to stretch a molecule of DNA. So it says one of the experiments that helped determine the mechanical properties of DNA involved attaching a bead to each end of a long strand of DNA and stretching it. A force versus extension graph of this experiment is shown at the right. The y-axis shows the force in piconewtons, and the x-axis shows or plots the stretch per base pair in newton meters. At low forces below 3 piconewtons, the DNA molecules behave like a Hookean spring. So we have really just knowledge that our y-axis is force and our x-axis is our kind of displacement or extension or compression, right? Or actually in this case it's just extension. So just kind of like the displacement that we have for this spring, right? And so if we remember with Hooke's law, it's F equals kx, right? And technically it is negative kx since spring force is a restoring force. But the idea here is that in general there is a relationship between force and the displacement that you have for the spring, and that they're related by F over x is equal to k, and we're going to get there in a second here with the relationships. But for part A, it's asking what physical quantity related to the mechanical properties of DNA do you obtain from the slope of the graph at low forces? So if you look at the slope of the graph, what are we getting here for the physical quantity? If we look at the slope, so our slope, right, remember is, it'll be the change in y over change in x, right? So if we have change in y divided by change in x, well, what's our y variable? Should be just force, right? Yeah, exactly, force. So our y variable is force. And then our x variable is extension, right, or the distance, and that's the same as x, right? And so remember what I said earlier, where f is equal to kx. Well, if f over x is equal to k, then the physical quantity related to the slope that you get is just, like Christian said, the spring constant. Right? Just the spring constant of DNA. Yeah, literally just they're asking you what physical quantity related to the slope of the graph at low forces. Oh, no. They're just asking you in general. Because remember, like, we can calculate the slope here, and we can calculate the slope there, and slope here, for example. But regardless, the slope in general gives you the spring constant. Yes, if we say the slope, for example, if the slope here is like, I don't know, 2 or 3 or whatever, right? Then we can say, okay, then a slope of 3 or 4, for example, will be denoted in the enthalpic region, for example, right? But in general, the slope that we have is going to be force over the extension, right? And so that's going to give us our spring constant for DNA. Make sense for part A? So just asking you like a variable relationship. Sound good? Yeah. Yeah, you can just say spring constant for DNA. Yep. But yeah, that's pretty much it. I'm not even sure if there's like, I'm wondering maybe if there's a specific like name for the spring constant of DNA. Like, is there a specific property of that? Like, or is there a specific like adjective for it? I don't know. But I would just say spring constant of DNA. We never got this problem, so I'm solving it pretty much like for the first time with you guys anyway. So um, the way I just kind of wrote it down was spring constant. I don't have like an answer key or anything to check, but I would just describe it as a spring constant of DNA. I looked it up briefly earlier, and yeah, all I'm getting is spring constant of DNA. I'm not sure if there's a specific name for it other than that, but I mean, they're just asking us about relationships between force and the displacement here, right? For the slope. So the slope is just giving you the spring constant. So yeah, that's all I would say for that, to be honest. But in a sense, remember, like, spring constant will measure like stiffness of a spring, right? And so if you have a higher spring constant, then the spring is a little bit more stiff, right? So spring constant for DNA, I guess, would just be like stiffness of DNA, which doesn't make a lot of sense off the top of my head, but I guess we'll just take it as is. Spring constant for DNA, that's the relationship that you have. So that's part A. Part B, right, is going to be asking something a little bit similar. So for part B, it's asking what physical quantity you obtain from the area under the force extension curve between any 2 points. So if we're looking for the area, right, if I wanted to say like, okay, let me find the area underneath the curve from here, say this point to this point, right, this little shaded area here, right, if I wanted to figure that out, then I'm technically taking force times, well, xx, force times your displacement, right? Now what is that? Force times displacement. If I'm taking the area underneath the curve, right? If I'm multiplying force times displacement, what am I getting? Work, right? Excellent. Yep. Because remember, work is force times displacement like this. They denote it as d. You can say the same thing, extension, if you wanted to. You can say the variable is d as well, the distance or the extension away from the original position, right? But the idea here is that force times any distance or displacement, right, is going to be equal to your work. So you can just say, and they're asking you here like what physical quantity in general, right? So it would just be work that you get. Work when you multiply the force times extension, or you find the area underneath the curve. But yeah. You could, if you wanted to be more specific, yes, absolutely, because the spring force here is not constant, right? It'll change over time. The reason why is that since it's F is equal to kx, right? Well, you can see based on the fact that we know that k is your slope, the slope constantly changes, right? It changes throughout that whole graph. And so if that spring constant is constantly changing, as the extension changes as well, then your force is going to always be different, right? Or at least it's going to vary throughout, right? So if it varies throughout, then you're not going to have a constant force. And so you can say work due to constant forces if you want to be really specific. So either way, you can say work. You can say work due to not constant forces, right? Either way works. It's just work in general. But yeah, you can say, if you want to, you can add work due to non-constant forces or work due to the spring force. But yeah. Makes sense for part B? Any questions at all? Nope. Okay. Part C now is where we get a little bit more into the math aspect, right? So we have Consider the extension of DNA from 0.28 to 0.32 nanometers. On the graph, shade the area corresponding to the amount of work done to achieve this extension. Compute the work done in units of piconewtons per, is that? Okay. Gotcha. That makes more sense. I was so confused why they just put a period there. Okay, fair enough. Piconewtons times nanometers per base pair. And that works out excellently because then we don't have to do any conversions either. So we can just literally take these units along with these units, and we don't have to do a lot of work with conversions. So you may approximate the shaded area by the shape of a triangle, right? Okay, excellent. So they give us 0.28 to 0.32. So 0.28, what's it? This is 7, 8, 9, yeah, 30. So 0.28 right there, all the way to 0.32, right? So roughly this little triangle here, right? Now, once again, we need to find the area because remember the area underneath the forced extension curve, force times distance is going to give you work, right? And so for the area here, right, we have, let me mute real quick just because please just if you guys like have any background noise or stuff, just remember to mute. Sometimes it'll leak in, and I was trying to like focus there and I lost my train of thought. But anyway, so we have 0.28 meters here, 0.32 there. So that's, we can figure out our extension. That's going to be like our base for our triangle, right? And then our height here is going to give us the force, right? So roughly, kind of trace this over, we can see that it's around what? So this is 2, 4, 6, 8, 10, right? This is about 2 piconewtons here, right? And then our extension here from 0.28 to 0.32 nanometers is 0.04 nanometers, right? That's the length of that base of the triangle there, right? And our height is going to be that 2 piconewtons. Well, if we want to find the area of a triangle, remember area of a triangle is half base times height, right? So if our base was 0.04 nanometers and our height was 2 piconewtons, right? Then we just multiply that together and we should just get 0.04 piconewtons times nanometers like they want, right? And that's the area that we get underneath the curve from 0.28 to 0.32, and that should give us our work, because remember the work is the force times the distance or the displacement, right? So if we look at the area underneath the curve, that's how we can get it. I said it's in increments of 2. Oh shoot, my bad. Yeah, I even said it out loud and I proceeded to write the wrong thing at 2, 4, 6, 8, 10. So this should be 4. My bad. Yep, 4 piconewtons. Thank you for catching that. So it actually should be 4 piconewtons here, right? So what is that? 0.8. Piconewtons times nanometers. That look better? Cool. 0.05? Oh, you mean... Oh, 5 piconewtons. Okay. I mean, yeah. I mean, honestly, if you go 4 or 5, you're going to get about the same answer. So, and like I said, they're not going to like dock you points if you have 5 either, because they want you to approximate the shaded area, right? So there's going to be leeway for sure. So it's an approximation. They're not going to count you off for having like, oh, if you said like 3.9 or 4.1 or whatever you did, right? They're not going to like destroy you about that. they're going to be pretty lenient with it as long as you show that you understand that area underneath the curve is going to give you your work. And so you can say this is equal to work, right? And that's equal to force times distance. So as long as you show that understanding, then you're good. Otherwise, the value is like just an approximation, so it's up to you. But part D is the same thing. It's just that now we're doing it from 0.42 to 0.46 nanometers. So we know that once again, work is the area. So that's half base times height, right? So that's half. And our base, you're going to remember our base is the change in that distance right there. So that's another 0.04 nanometers, right? Now we just have to figure out what's our height. So for our height, what is it, from 0.42, so let me erase this real quick, 0.42 to 0.46. And so let me kind of draw this upwards like this. It's going to be really tough, but roughly like that. That's a little triangle that we need to calculate, this little part right here. And so this is about what? I'm so stupid. Okay. No, I totally, like, I was so used to doing the triangle here, and then I moved over here and I just forgot about this entire space right here. Technically, if we wanted to be very precise about it, we can do it as an area of a trapezoid, so my bad. I don't know why I said area of a triangle there, but it should be area of a rectangle because you have all this space down here. My bad, my bad. Otherwise, like here, you have these little small triangles, and so you can calculate the area like this. So if we can just find the height here, right? That's what, say like 62, maybe 63, depending on, I can't make it any smaller, but let me see here. $61. I got about 62, but yeah, 61, 62 is pretty close. I would say 62, but some people are using 64. So here's 60, 62, 64 is up here. I mean, once again, it just kind of depends on how you're looking at it, but I got 62. Once again, just depends on you. If you can show that roughly you get 64, that's fine too. But it's just going to be base times height. And so 0.42 to 0.46, that's 0.04 nanometers for our x distance right there. And then our force, 64 piconewtons, right? So once again, it's not the area of a triangle. That's my mistake. But it should be 64 piconewtons times 0.04, and that gives us around 2.56 piconewtons times nanometers, right? Around that range. See, now I think I'm just not focused today. I said I was going to use 62, then I proceeded to use 64, and it's just not a good night so far. This is not the greatest start. 2.48, that's what I should get. 2.48 piconewtons times nanometers is what you should get if you use 62. If you use 64, it's 2.56. So there, I compromised. I showed you both ways for those of you who wanted to use 64 and for those of you who wanted 62. You know what, Matthew, just for you, I'm going to calculate 61. 61 times 0.04, you get 2.44 if you use 61. There. Now everybody's happy. So there. It should be 2.48 if you use 62. But hopefully now we're all on the same page of the relationships with a type of graph like this. I'm like very confident that you're gonna see at least one type of instance where you have to analyze a graph like this on the exam. But yeah, it should be slope on a graph like this force divided by the extension, right, or the displacement. That's going to give you your K, your spring constant. And then the area underneath the curve, so if you have this little triangle here, or if you have this big rectangle here, or even if they wanted you to calculate from here to here, then it would just be this whole rectangle, right? Area underneath the curve is going to be force times the extension or the displacement, right? Force times distance is going to give you your work. So hopefully that all makes sense for problem 1. Sound good so far? Any questions at all? Okay, cool. All right, so I don't think it's going to get any better for me here. If I messed up on problem 1, then I sure as hell am going to screw up the rest, I think. I don't have any confidence. I wish I had any faith, because this problem 2, problem 3, and problem 4, you're going to see a lot of these, well, I guess I wouldn't say a lot, but maybe 1 or 2 problems on the written for the exam, and they are hell, because especially for this type of problem right here, we had one where, yeah, you were starting like at the top of the hill or something, and then at the very end you had like a spring that you like had to hit, and that was going to stop you, so you had to calculate like different energies at different points in the system and stuff. And so you can't just like have like just a starting and just an initial and just a final. You have to like really be good at breaking things up, and breaking up the points with different like energies at each point depending on what happens. Because here, for example, you're all, or at least when you start up here, it's all potential, and then when you start moving, well, you have still potential and you have now some kinetic. And then when you slide down, for example, you have a decrease in potential, right? And you still have kinetic because you're going downwards. So by the time you hit C here, if you made this bottom as your 0 point and this height, oh, am I frozen? Okay, let me reshare real quick. All right, can you guys see that better? Okay, cool. Yeah, so if you use C as like your arbitrary 0 point, and B here just in general is like your height, right? Then at 0, you're going to have 0 gravitational potential energy, and at the top here, you're going to have maximal. And so as you go down, there's a conversion from gravitational potential energy to kinetic energy, right? And so just figuring out how to kind of calculate things to switch in between all these different points, because then if they add a spring here, for example, well, then everything is kinetic up until it hits the spring. And so like all of your, because this is based on conservation of energy once again, like conservation of mass, like all those conservation type laws. So whatever energy you start with, right, it's conserved throughout the whole process, assuming that nothing is lost due to like friction or anything, or no heat energy is lost throughout the process. And usually we try to assume that's what's kind of going on, but this is where they pull some stuff where they'll add like friction or something, and so that does work on the system. And then you have like a decrease in energy in a sense. Not really a decrease in energy, it's still, the energy is still there, you can calculate and account for everything. It's just that work is done on the system, and so the I guess the energy that you can calculate other than the energy that's lost to friction or heat, right, is a little bit different. So yeah, just honestly trying to figure out different points, how to calculate the energy for each point is just takes a bit of a learning curve, and there's a lot of math involved. So I don't want to scare you guys, but like it just spend time on it. Like if you thought torque was difficult in a sense, or any of that, does not compare to the energy stuff in my opinion, because the energy, there's a lot going on and the problems are super long. But yeah, hopefully I can try to help. Yeah, there's a lot of work that you have to do to understand work. So yeah, we can move on to problem 2 now. So problem 2 is roller coaster and spring. It says a roller coaster moving with an initial kinetic energy of 1500 joules goes down a hill. This is why it's also very difficult because there's a lot of information that they give you in these problems. So you have initial kinetic energy is 1500 joules, right? Ki is 1500 joules. Okay, cool. And then it goes down a hill and through a loop-de-loop as shown. The roller coaster then moves along a level track and stops by compressing a spring with spring constant. K is equal to 25,000 Newton meters. This is the kind of idea that I was talking about earlier. Well, they're going to have you start at specific height, you go down, things are converted into kinetic, and then somewhere at the end you have like a spring or something. So I remember they included all of that in one exam problem, and it was just difficult to kind of account for everything. But now the mass of the roller coaster is 1,500 kilograms. Okay, cool. Height is 45 meters, right? So whenever we have height, you want to think about potential energy, right? Especially gravitational potential energy. So if we started at a specific height, we have gravitational potential energy if we make this bottom point 0, for example, right? Now, the idea with gravitational potential energy is it's really in the name, right? It's the potential energy. It's the potential to move, right? So you have a specific potential energy. You have the energy or the potential to start moving. So whenever you are moving an object from as arbitrary 0 point and increasing its height, moving it upwards, you're going to increase its gravitational potential energy, right? So as it gets higher and higher up, it has the greater potential to like move and convert itself to kinetic energy, or for that object to start motion and have kinetic energy. So think of like maybe a rock, or maybe like if you're watching a movie or something, if there's a person like standing on top of a cliff, right, and they seem like they're off balance or something, well, they have a lot of potential energy to start moving and they fall off the cliff, right? There's a lot of potential when you're up top, when you're very high up in the air, right? Now, it says the loop also has a radius of 10 meters. So if this loop is 10 meters for its radius, r is equal to 10 meters, well, you might think, well, okay, it's a circle, right? 10 meters, like, what do I care about a circle? It doesn't seem like I should be doing any centripetal acceleration or centripetal force or anything like that, or angular velocity. Like you start questioning, like, okay, why did they give me the radius, right? We'll just think once again, radius, whatever it is, right? You have a distance, right? So you know that from the center of the circle, from the center to any point on the circle itself, or at least to the edge of the circle, essentially. So from the center to the edge of the circle at any point on the edge, that's your radius, right? So that's a distance from the center to the edge of the circle. So if we think about it, right, we can say that, okay, well, this radius is 10 meters, but what does that mean? Well, it means that from the bottom here, from this bottom point to the center, it's 10 meters. And then from the center to the top, it's another 10 meters. So in reality, we can say that, okay, well, at the top of the loop, it's 20 meters in height total, right? At the bottom of the loop, we can make that our arbitrary 0 meter point. And in the middle here, we can say that it's 10, right? Rarely ever do we consider things that are in the middle, which is usually, if you have a problem like this, the top of the loop and the bottom of the loop are the most important measurements that you have to watch out for. But it also says we can neglect the effects of friction on the roller coasters. That's great, right? So we don't have to calculate any friction. No friction is like factoring in or doing any work externally on the system. So we have information about kinetic energy. We can get information about potential energy at the top here, right? The idea here now is that we have to recognize too that there's no friction. So usually when we're doing friction, I at least prefer to calculate friction as external, as doing work on the actual like system, as opposed to internalizing the friction or that thermal energy, right? So if you were to internalize everything, if you were to internalize the concept of energy, then that means your work is 0. If everything is internal to the system, no work is being done, work is 0, right? And so your energy would just be, because remember, work is equal to the change in energy, right? So if work is 0, right, then we have here, and we know that the change in energy is actually equal to pretty much like all the sum of the energies that we have in question, right? So we have some change in gravitational potential energy, some change in kinetic energy, and then we have also thermal energy due to that friction. Theoretically, if there was friction, right, that would contribute to that change in energy overall. Now, this would all equal 0, right, if there is no external like force or external external force causing any work, right? Because otherwise, if there's no external force, there is no work, right? Then the change in energy should be 0, because energy would then be conserved. There's nothing that would be taking away essentially energy from the system. Otherwise, if we were to, and this is assuming once again thermal energy here, that's if we assume that it's 0 too, because they said that the you can neglect the effects of friction, so there shouldn't be any change in thermal energy or no friction in this case, right? So really our energy should just be equal to, our change in energy should be equal to the change in gravitational potential energy and kinetic energy. If there was work done on the system, right, due to friction, for example, then we would calculate that using W equals FD cosine theta, right? You would have to calculate that. Let's say if there was a rough patch here, for example, and they gave you a coefficient of friction and whatnot, all the necessary information to figure out friction, then you can calculate the work due to friction. That would be against the movement of the object, right? And then that work is equal to your change in energy. And we know that the change in energy is the sum of all the energy forces that are in question here, or the energies that are in question here. So there's a change in gravitational potential energy and a change in kinetic energy. That's equal to the change in energy, and it's equal to the work done, right? And so in that case, then you can, figure out how much work is done, and then maybe, do some other calculations that you need to. But that's in general the idea here with internalizing versus externalizing energies. So if you internalize all the energies, you internalize all the forces and stuff, then you have work equal to 0, and then you're just trying to figure out the energies that are associated: gravitational potential energy, kinetic energy, thermal energy, stuff like that. That's if you internalize everything. If you externalize some aspects, right, then there's going to be external forces that would be acting on the system, right? External forces causing work done on the system that would detract or take away energy from that system. And then in that case, there would be a change in energy. There would be, for example, if the work was due to friction, right, and you lost, for example, negative 600 joules, right? If there was work equal to negative 600 joules, then your change in energy is negative 600 joules, right? Your change in energy is negative 600 joules. So in that case, you can say like, oh, well, 600 joules of the system was lost due to the thermal energy from friction, right? You can account for it, you can calculate for it. In a sense, energy is still conserved because, we can add up all those components and we can get 0 in the end. But the idea here is that if we're looking at the energies here, like gravitational potential energy and kinetic energy, we can see that from that internal set of quantities, from that internal set, 600 joules was lost due to friction because there was an external force acting, doing work on the system. Otherwise, if we internalize everything, right, if everything is within the circle, K, UG, E thermal, right, if everything's within the circle, it's 0 work. If there's some stuff outside of the circle, right, so we have UG and K here on the inside, and you have some work on the outside, well, work is going to do some work, right? So you have some kind of force externally that's going to do some work that's going to detract or take away energy essentially from the system. So that's kind of an overview. Sorry for the tangent there, but it's very important to understand that concept. But now we can move on to A, because now they're asking what is the change in gravitational potential energy of the system from when it starts at the top of the hill to when it's at the top of the loop, right? So what happens here? We start from the top, we go down like this, and then we go here, right? Now with gravitational potential energy, doesn't matter the path that you've taken. Does the path taking matter at all? No, exactly, right? You're just concerned with final and initial positions. So if we wanted to figure out the change in gravitational potential energy, there's a UF and a UI that we have to calculate. UF minus UI, final minus initial energy, right? And that's going to give us our change in gravitational potential energy, right? So we know that gravitational potential energy is equal to mgh. So there's a final height and there's an initial height as well, right? And that's how we can figure out our change in gravitational potential energy. They gave us the mass. They said the mass of the roller coaster was 1,500 kilograms. Gravity is obviously 10 meters per second squared, right? And then we have our heights that we can figure out. We started initially, right? We started initially at 45 meters. And once again, we're considering this as our arbitrary 0 point. We're naming the bottom of the loop here as the 0 point. And then the top here would be our 20-meter point of the loop. And then this is 45, right? So if our initial was 45, our final was 20, and this is all relative from the bottom. And yes, you can just say UG is equal to mg delta y if you wanted to. Either way works. But yeah, if you take 1,500 kilograms times your 10 meters per second squared times the final height. Remember, the final height was 20 meters, right? That was at the top of the loop. We want to figure out the change in gravitational potential energy from when it starts at the top of the hill to when it's at the top of the loop. So our final is at the top of the loop, which is 20 meters up from the bottom of the hill. And then we have another 1,500 kilograms times 10 meters per second squared. And then our initial height was 45 meters, right? That was at the top of the hill. You can also say 1,500 kilograms times 10 meters per second squared. And then you can do basically, 20 minus 45, right? Your final minus initial, and that's your height. So you should be able to get negative 375,000 joules, I believe, for that piece right there. That would be your change in Yep, negative 375,000. Yeah, if you had positive, then you might have just switched these around, for example. You made your final 45 and your initial 20 or something like that. But yeah, it should be negative, right? And that makes sense because as you go down, right? Let's say this was kind of like this right here. This was the hill, right? So if you started up top here, you have only potential. The roller coaster isn't moving, right? It's only potential energy. It has the potential to move, right? So let's say it started off at, I don't know, 600,000 joules, right? For example, that was its potential energy, its potential to move. As soon as it starts moving, right, there's movement, there's speed now, right? There is kinetic energy. So the idea with conservation of energy is that, once again, the change in energy, if everything is internalized, right, should be zero. Energy should be conserved, right? So if I start with 600,000 joules of gravitational potential energy at the top here, once I reach this bottom point and I'm moving on, let's say if there wasn't a spring here, if I just continued moving on, for example, no friction, nothing to stop me basically, then I should end up with 600,000 joules, but kinetic energy, right? So the idea here is that as you drop in height, because remember UG is equal to mgh, as the height goes from 45 to 40 to 30 to 20 to 10, right, there's a decrease in gravitational potential energy, right? But as you fall down, right, just think of it as, as a roller coaster moving down, right? Or if you're skiing down a hill, for example, you might start out a little bit slow, but as you go down the hill, right, your speed starts to increase, right? Speed starts to increase, and then, you know that kinetic energy is equal to half mv squared. So as your speed increases, your kinetic energy increases. And it increases in a way that it kind of takes from the gravitational potential energy and adds to the kinetic. So as UG drops, kinetic energy will increase pretty much by the same amount. So if I dropped negative 20 joules, right, if I went down 20 joules from my gravitational potential energy, I should see an increase of 20 joules for my kinetic energy. That's the idea. So it's like one sucking the power from the other. That's the idea. When will we use the formula W is equal to negative change UG's? So you mean like, okay, so W, so work is equal to negative change in gravitational potential energy, and then that's negative UGF plus UGI. I can't remember what's the exact situation. Shoot. Let me get back to you on this one. I know exactly what you're talking about. I just can't remember fully what the problem was, because I know it was a problem on the slides for the professor. So remind me at the end of the session to go over this one again. But I know exactly what you're talking about. I just can't think of it off the top of my head. What situation we'd use this in. But yeah, just remind me. You said the subscript was conserved, so CONS. Let's see here. Oh, okay. I think I got it now. So if I guess okay. So our energy, for example, would be equal to change in kinetic plus change in gravitational potential energy, right? Now, if work was externalized, right, then work would equal that change in energy. Yeah, for some reason I'm frozen on this one. But I know exactly what you're talking about. I just can't envision it for some reason. But I'll get back to you at the end. Yeah, go ahead, Matthew. You had a question. We were on problem A. Just Christian had a question real quick about when to use that specific equation. I know, like, I can see the equation right in my mind, and I know I can even I remember like what the problem was, kind of. I just can't remember what was the context that made us use it. Because I remember that it was like work is equal to delta K, and then you had to like substitute it where then work was equal to negative delta U or something like that. It might have been, oh, I'll tell you what it was. Okay, so I think it was that since energy is conserved, right, if you were to internalize everything, so 0 is equal to delta K plus delta U, then delta K is equal to negative delta U, which makes sense, right, because the change in kinetic energy, right, if there's an increase in kinetic energy, then that should mean a decrease for that change in gravitational potential energy. Like I said before, right, if I gain 20 joules for my kinetic, I decreased 20 joules for my gravitational potential energy, right? So in that case, your change in kinetic should be equal to your change in gravitational, or opposite the change in gravitational potential energy. Now, if you were to externalize work, right, where you had W is equal to, just energy is equal to, delta K plus delta U. Well, the idea here is that now, right, delta U, you can't even calculate for it anymore, right? And the reason why is that delta U, when you externalize work, right, or when you externalize the gravitational force, that's what I mean. If you externalize gravity now is a force that is acting externally, doing work on the object. If that's the case, then we can no longer internalize gravity. We cannot make gravity part of the system. Remember that circle idea I was talking about earlier? Then remember we used to have UG on the inside of the circle and kinetic on the inside. Now, as soon as we externalize the concept of the force of gravity now does work outside of the object, right? Or external to the object. It does work now. And so UG is now outside of the circle. Once it's outside, we can't calculate for UG anymore, because force of gravity now is doing work external to the object, right? So once we externalize the force of gravity, it's doing work on the object. We can no longer calculate for delta U. So in that case, whatever work that gravity is doing, right, is going to be equal to the change in kinetic energy that you observe due to that work. And so in that case, if we look at our equations here, we said that this is internalizing work. So internal, if you internalize work is zero, energy is conserved. You can calculate for kinetic energy and gravitational potential energy. You can see that any increase in kinetic energy is equal to the decrease in gravitational potential energy. Now, if we were to externalize work, then work, right, has to be equal to that change in energy. It's no longer zero, right? Work is technically force of gravity, right, is doing work on the system externally, right? If it's a ball, right, force of gravity is acting on the outside. So UG is outside of the circle, in a sense, right? So we can no longer calculate for it. Once that UG is outside the circle, UG becomes outside now, you can no longer calculate for it, right? You cannot use that internalization of gravitational potential energy anymore. So force of gravity does work externally on the system. It detracts, right, from the energy of the system in a sense, right, because it's doing work externally. And then that's going to be equal to the change in kinetic energy. So you can see here that work is then equal to delta K. And then what did we say before? Delta K is equal to negative delta U. So W is equal to negative delta U. And so that's what you were asking about, Christian, where you said, when do we use W is equal to negative delta U? And then that's equal to negative UGF plus UGI. Does that make sense? So that's another very, very, very important concept, the internalization versus externalization of different forces and stuff that would cause you to either be able to calculate for gravitational potential energy or not be able to calculate for it. So hopefully that little bit there made sense. But that is probably the hardest concept to understand with regards to work. The internalization versus externalization of forces and how that can allow you to calculate for potential energy or how it does not allow you to calculate for it. But if it's external, then you can't calculate for potential energy. If internal, then you can. So if you internalize gravity, you can calculate. If you externalize gravity, well, it's doing an external force now that's going to be doing work on the object. And then that work detracts from the energy of the system. So energy is no longer technically conserved. In a sense that, it's going to detract from the system, but you can still account for it. But yeah, hopefully that kind of cleared things up a little bit. But I'll definitely go over it in the quiz review session to emphasize that concept a little bit more. That is probably the most important and the most difficult concept to kind of wrap your head around with regards to energy stuff. But yeah. For B now, it says, what is the velocity of the roller coaster when it's at the top of the loop? So we want to figure out velocity at the top of the loop, right? So once again, it would be better for us to internalize gravity, right? Because that way we can calculate for stuff like gravitational potential energy, and we don't have to worry about the work that force of gravity is doing external to the object. So if we internalize gravity, then work is equal to 0, right? And that's equal to delta E. And then that's equal to delta K plus delta UG, right? So in this case, right, we can see here that if this whole thing is 0, right, then delta K should be equal to negative delta UG, right? So whatever increase I see in kinetic energy is equal to my decrease that I saw in my gravitational potential energy. So if I'm trying to figure out what happened at the top of the loop, this is the same as what happened at A, right? I went from top of the hill to the top of the loop, right? So I know that kinetic energy is equal to half mv squared, right? But there's this change in kinetic energy. So there's half mvf squared and then half mvi squared, right? This is kinetic final minus kinetic initial, right? And then the change that I see here, right, there's an issue with this a little bit. Now, the issue is that, okay, well, I calculated for the change in gravitational potential energy, and that change was negative 375,000 joules, right? Well, what this is telling you here, negative delta UG, you wouldn't just say, oh, this is negative of negative 375,000 joules, right? You would not be able to say that. And the reason is that the way that we're writing this, where I guess like the issue is here, it's more like with this aspect here, that we're assuming that the change is positive in a sense. So we didn't add like a direction, right? So we got the direction here. And so if we're integrating direction in this equation right here, this part right here is denoting that there's a decrease, right, for our gravitational potential energy. If there's a decrease, right, then we can just say there was a decrease, so this negative sign denotes decrease, and then that's a decrease of 375,000 joules, right? That's what this is saying here. For every increase that we see in kinetic energy, there's an equivalent decrease, right? So if I upped my kinetic energy by 20 joules, I should see a decrease of negative 20, right? Or a decrease of 20. I can't see a decrease of negative 20. That's what I mean. So if I say negative 375,000 joules, right? And this was positive 375,000, then for the increase that I saw for my kinetic energy should equal the decrease that I saw, right? So I'm saying should the negatives cancel out? One sec. So let me just double check my math here in my head to make sure that all checks out. Okay, I see. Okay, so I made a mistake. My bad. So if we were to make this, okay, so if we did half times 1,500 kilograms, and this was VF squared that we're trying to figure out. This is the final velocity at the top of the roller coaster, or at the top of the loop. And then our kinetic energy initial, that was 1500 joules. Okay. I think I just messed up somewhere here that I was thinking of something different. But yeah, this should then be, okay, so this should be 375,000, my bad. 375,000 joules there. And I think that accounts for everything in that case. Yeah, okay, so for some reason I just messed up signs somewhere along the line where, I mean, it obviously makes sense. If you start out here, right, as you go down, you're going to increase in your speed. And so there should be an increase in kinetic energy. And that increase in kinetic energy should equal the opposite of the decrease in gravitational potential energy. But yeah. And even if you are unsure about how all this works, and it's just maybe a little bit easier to just go ahead and do that, you have a change in energy, right? That's EF minus EI. And if that's equal to 0, right? So EF is equal to EI. And so let's say like KF plus UGF is equal to KI plus UGI. And then you can kind of figure things out that way. So either way kind of works, but maybe the second way is a little bit easier because it just eliminates the idea of messing up negative signs and stuff. But anyway, if you go ahead and solve for this, I think you should get for your VF around 22 meters per second or so. 22.3 maybe. But yeah. So our initial velocity, remember, like this is our KF and this is minus KI, right, for delta K. So this is our initial kinetic energy. This initial kinetic energy was given to us. They said initial kinetic energy is 1500 joules. So we don't even have to know what the initial velocity here is. We don't have to calculate for that because we can just say that this whole thing is 1500 joules. Does that make sense? Okay, cool. But yeah, VF should be around 22 meters per second. I don't know what I was doing there where I messed up the signs at the beginning. Apologize for that. Anyway, part C is now asking us for probably the most difficult step of them all. And it's saying the spring at the end of the track eventually stops the roller coaster and the spring gets compressed an amount equal to delta L, right? Determine the compression of the spring. So this is where I was talking about earlier where you have to break things up into different pieces, right? So first of all, right, we started up at the top here and then we went through this loop, got up to 20 meters here, and then now we're down back here at the bottom at 0 meters, and now we're traveling this way, right? So what I want to get at here is the idea that I'm going to have only kinetic energy here at the bottom, right? That makes sense because if I'm at the bottom here at 0 meters, mgh, if h is 0, then there's no gravitational potential energy at the bottom here. So I want to figure out, well, okay, I know at this point and onwards, it's only going to be kinetic energy, right? It's only going to be kinetic energy from here onwards, right? From this bottom point onwards. Now, once again, with the idea of conservation of energy, right? It should mean that whatever kinetic energy that I have here along this path, once I hit the spring, it's going to get converted all the way to elastic potential energy, right? Spring potential energy. So remember, if I started at the top here, if I started off with 600,000 joules, right, of UG, when I reached the bottom, 0, when I finally reached the bottom, I decreased 600,000 joules from the gravitational potential energy, and that all got converted to 600,000 joules of kinetic energy, right? So whatever you decrease from one, whatever power you suck from one, it gets converted into the other one, right? So if I went initially only gravitational, as I move downwards through the loop and all of that gravitational, once I hit the bottom here, has now become all kinetic. So I know that once I hit this spring, there's going to be conversion from kinetic energy to elastic potential energy. Well, I want to figure out just how much conversion that is, right? And then basically try to figure out then when I convert that kinetic energy into elastic potential energy, let's say that this is 600,000 joules of kinetic. The same 600,000 goes to elastic potential energy or spring potential energy. Well, if US, for example, is equal to 600,000, right? Well, based on the idea that US is equal to half kx squared, right? And I have this spring constant, then how much did it move by, right? That's the idea that I'm trying to figure out here. So I started off only with UG, then that decreased a little bit, right? Here, for example, there's a little bit more K, right? Go through the loop, I end up at the bottom. Now it's only K. And then I move along here, and now it converts itself to spring potential energy or elastic potential energy, right? So I want to figure out from this bottom point where it's only kinetic, and that's the easiest point right here to figure things out from because I'm only, looking at one type of energy, goes from kinetic to spring potential energy. Whatever decrease I see in kinetic, I should see the equal increase in spring potential energy. And so I just want to figure out when that energy goes to spring potential energy, what kind of change does it cause in the spring's distance, right? So that requires me to figure out what the kinetic energy is here at the bottom, right? So like I said, whatever increase that you see in kinetic energy, you should see that decrease in potential, right? So that means for the gravitational potential energy, I should see UGF minus UGI, right? And once again, since this is at the bottom and this is at the top, so there should be a decrease overall, and so that decrease with another negative sign should give you positive, and that makes sense, right? That was my mistake from earlier. Now, there should also be that increase in kinetic that we got from before, right? So, this is negative. And we have, 1,500 kilograms. And then times the change, or the acceleration due to gravity, and then we can multiply by the change in the distance, basically. And that should be negative 45 meters, right? Because you went from top of 45, that was your initial, and then here's at the bottom, your final is 0, right? So final minus initial should be that negative 45, right? That'll give us our change in gravitational potential energy. Now, that'll give us what the kinetic energy is equal to, right? That's going to give us our total increase in kinetic energy, basically, right? So if we calculate this out, what should we get here? So let me multiply this real quick. So this should be roughly 675,000 joules, right? So I saw a decrease of 675,000 joules, right, from gravitational potential energy, and then goes a complete increase of 675,000 for kinetic, right? Kinetic. Now, that's how much my kinetic is at the bottom, right? The idea here now is that all of that kinetic is going to go to spring, right? Because then the spring will get compressed a certain amount based on the amount of kinetic energy that was there, right? So if I go at 675,000 joules, we're assuming that this is frictionless, no energy is lost, right, to anything else. And so once we hit this spring, all of that kinetic energy, all of that speed that the roller coaster was traveling with, once it hits the spring will get compressed to a certain amount that will give us a spring potential energy that is equal to the kinetic, right? So once I hit the spring, the decrease that I see in my kinetic energy is going to be equal to the increase that I see in my spring potential energy, right? So that means then delta K should be equal to negative US, right? The increase that I see in my kinetic, or the decrease that I see in my kinetic, my bad. And this should actually be, like, in a sense, it should be actually the other way around. So negative delta K should equal your positive US, right? Because the decrease that you see for your kinetic energy should be equal to the increase that you see for your spring potential, right? So someone said they got negative 675. Okay, let me look this over once again, because I've made a mistake somewhere. I just know it because I hate this energy stuff as much as you guys. So let me look over my work real quick. Okay, so I don't know. I'm getting positive 675. Anybody else getting positive? I don't see anything wrong with what I'm doing so far. There should be an increase in kinetic energy from the top to the bottom. Yeah, I keep getting positive here. So, I mean, once you set this up, right? Once you have negative 675,000 joules, then should be equal to your final minus initial for spring potential energy. So if your final is, let's say, half, this is kx squared, right? So k is 25,000 Newton meters, and this is xf squared minus half 25,000 xi squared, and xi should just be 0, right? Because that's the equilibrium position. But yeah, then the negative wouldn't make sense because you can't take the square root of a negative, so I'm not sure what is going on here. Yeah, that's what we're doing. Because this would be half kx squared, right? And so I'm just taking the final minus initial of that. We got 375 for part A. That was our change in gravitational potential energy. Because we went from the top here, 45, to just 20. We're calculating now from 45 to 0. So you got negative by doing initial minus final instead of final minus initial. Okay, I see what you mean. I don't know why this is giving a wrong answer though. That's just what boggles my mind. But um, okay. Okay, if I just go back to the original, just idea of initial should be equal to final. So K initial plus U initial is equal to K final plus U final, right? Then my K initial is 1500 joules. My U initial was 1500 times 10 times 45, okay. And then K final, which is at the bottom of the loop technically, would just be half 1500 kilograms, yep. Or actually, no, KF is what we're trying to figure out. That would just be the kinetic energy at the bottom, technically. So KF and then plus UF, so that's at the bottom, that's 0. Okay. Well then, okay, it's still getting positive for that. So if we were to continue with the positive, now our initial is kinetic, is only kinetic, and our final is only going to be KF and USF, basically, right? And we can actually just say KI plus UI, and UI is 0, right? Plus KI. That was the 675,000 joules. And so, okay. KF is 0, and then that's equal to USF. Okay, that makes sense. Okay. So, I guess lesson learned. Forget the delta stuff because that's just going to throw you off. I would just go with EI is equal to EF because delta E is equal to the change in kinetic plus the change in gravitational potential energy or change in static or spring potential energy, right? So, and this is all equal to 0 because their energy is conserved. So EF minus EI is equal to 0. So just EF is equal to EI, and then just add, like, put in all your different energies. So if EI, right, your initial kinetic energy plus your initial spring potential is equal to your final kinetic plus your final spring potential, right? So I would just do it in that format instead of all the different deltas because that'll just mess everything up. And you can see here that I'm just screwing up the entire night with these stupid, unnecessary mistakes. So, once again, if we say EI is equal to EF, right? There's an initial kinetic at the bottom of that loop, an initial spring potential energy, and there's a final kinetic and a final spring potential energy, right? So just move this over here a little bit. In that case, our initial kinetic would just be equal to the 675,000 joules. That's our initial kinetic. Our initial spring potential would just be equal to 0, right? Because initially that spring isn't in contact with anything, right? It's at its equilibrium position. So if US is equal to half kx squared, that spring hasn't been moved yet. So the displacement is 0. So in that case, USI would be 0, right? And then that equals KF, right? So once that roller coaster comes in contact with the spring will get compressed and the roller coaster stops moving. So KF for the roller coaster would be 0, right? And then final spring potential would just be half KXF squared. So your 675,000 joules is equal to half times 25,000 newtons per meter, and then times this XF squared. And so then we can find out our XF. And let me calculate that real quick. Okay, 675,000 times 2 divided by 25,000. And take a square root. I believe you should get somewhere around like 7.4 meters or so. Let me double check just to be sure. Yep, I got 7.36 is what I got exactly. So yeah, 7.36 meters. It's about right. So yeah, I think it would just be better in general to forget this type of notation here because it'll just throw things off, and just go with the energy initial is equal to energy final, and then that way you can calculate everything out. Otherwise, if you start doing the delta stuff, I mean, sometimes it functions excellently, and other times it just kind of throws you off with the signs and the directions of stuff. But EI is equal to EF is surefire way to get the right answer. So I apologize for the insane amount of time we spent on that problem. Mm-hmm. 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 Yep. Yep, for the kinetic energy. 675,000. Yeah, because there's nothing in contact yet with the spring. The spring is at its equilibrium position. So remember that spring potential energy is equal to half times your spring constant times the displacement that the spring was like compressed with, right? So if we want to figure out how much the spring got compressed by, right? Well, if our final kinetic energy, right, is 0 because once you hit the spring, the roller coaster stops moving basically, right? And so now you want to find out what your final spring potential energy is. If its initial was at equilibrium position, right? If it was unstretched, uncompressed, then it's at 0 here for USI. For USF is when it is compressed, and so that's when we try to figure out what that amount of compression is, right? So half kx squared, and then we can find x to figure out how much this thing was compressed by. Sound good? Okay, no worries. Yep. Okay, so I'm gonna try to move through these next problems a little bit faster, but we'll see. Problem 3 is energy and work done by friction. So a 27 kilogram child goes down a straight slide, inclined 38 degrees above the horizontal, which is 2.5 meters long. So this whole thing here is 2.5 meters long, right? And it's inclined 38 degrees above the horizontal. Okay, so there's friction between the child and the slide, and the magnitude of the kinetic friction force on the child is 72 newtons. The child slides all the way down to the bottom of the slide. Okay, so the distance basically of the slide is 2.5 meters, right? And then the kinetic friction in this case is 72 newtons, right? Okay, so now for part A, they want us to draw a free body diagram for the child, and next to the diagram indicate the direction of the child's displacement. So since the child is traveling down this way, it's kind of a tilted coordinate. So we can indicate tilted coordinates here to the right. We could say this is the y-axis and this is the x-axis, like that, right? Now we have force of gravity for sure, and then we have normal force, right, along that tilted x-axis pointed perpendicular to the surface. And then we obviously have kinetic friction acting against the child along the negative tilted x-axis. Did I say x-axis for normal force? I meant y-axis, I think. And then you have your distance, right? The child is moving this way along the positive tilted x-axis along the slide, right? Those would be your forces there for the free body diagram. Now, for part B, they're asking us what the work done is on the system by the friction force, right? So work done by friction, basically, remember work is FD cosine theta, right? Well, they gave us the force of friction, right? They said that was 72 newtons, and they gave us the distance, right? The child slides along the distance of the slide, which is 2.5 meters. But what's the angle? What's the angle at which this friction force is acting? Yeah, it is 180. So cosine 180, and the reason why it is cosine 180 is that if friction force is acting this way, right, this is along the negative x-axis, right, and her distance is this way, well, then the angle is 180 degrees, right? Kinetic friction is acting directly against the intended motion of the child, right, at 180 degrees. So if this, once again, this is a tilted x-axis, right? She's moving downwards in the positive x-axis. Kinetic friction is directed directly opposite along the negative x-axis with no angle of inclination for that kinetic friction, just along that tilted x-axis. So it should be cosine 180, because cosine 180 then gives you -1. So 72 newtons times 2.5 times -1, right? That gives you -180 joules for B. That's the work done by the friction force. So the friction takes away 180 joules from the system, essentially, or does 180 joules of work on the child. So there's a decrease of 180 joules of energy there. Does that make sense for part B? So you're saying like, wait, can you say that again? Because I just got so confused there. So you're saying like if you use this hypotenuse, I mean this is given to you, or so this is 2.5, right? No, I don't think they even... hold up, did they give you the height? Let me read it again. So 27 kilogram child goes down a straight slide, incline 38 degrees above the horizontal. No, I think they're referring to the length of the slide here, not the height. Because otherwise, even for part C and for part D, they want you to figure out gravitational potential energy, and you don't have a height there. Yeah, no, you can figure out the height later, though, using what you said, Pythagorean theorem and stuff, or at least trigonometric functions. That's what I mean. Because if this thing is 2.5 and you have this angle here, you can get the height using trigonometric functions. They're just saying here that 38 degrees above the horizontal, and then the straight slide is 2.5 meters long. But yeah. Now when they're asking you for the change in gravitational potential energy, right? So the change in gravitational potential energy, that gives us mghf minus mghi, right? So we have a mass of 27 kilograms for the child, right? And then times 10 meters per second squared for the gravity. And then her final height is at the bottom of the slide here, which is 0 meters technically, right? We can make that our arbitrary 0 point. That's the bottom at 0 meters. And then minus another 27 kilograms times 10 meters per second squared, and times the initial height, right? And the initial height, we can figure that out using trig functions, right? So if that slide was 2.5 meters long and the angle is 38 degrees, if we want to figure out height, right, we can just take sine 38 is equal to, this is our height over 2.5. So height is equal to 1.54 meters. And then we can make that the height initial, right? That's the top of the slide there. If this thing is 2.5 meters, the angle is 38 degrees, this is our height. Then sine, which is opposite over hypotenuse, opposite to the angle, which is our height, divided by the hypotenuse, which is 2.5. So sine 38 times 2.5 should give us our height there. And the height is 1.54 meters. So if we calculate this out, then you should get around negative 415.8 joules, I think. Right? That's about what I got for part C. Sound good? Okay. Now part D is saying if the child starts at rest at the top of the slide, determine the speed of the child at the bottom of the slide, right? Now, thing is here, we have work done on the system by the friction force, right? So that kind of takes away 180 joules from the system. So we can think about this work as being kind of a thermal energy, right? Or the friction force here as being your E thermal. So when we have this work, remember I said we can't really, if we want to externalize work, then we no longer are able to, actually, well, I'm going to say, so my bad. So that's, if we externalize work due to the force of gravity, then we can no longer calculate for the gravitational potential force. But work here is done by friction, so we can do that. That's fine. But the idea here is that, once again, work is equal to your change in energy, and that's equal to change in kinetic plus change in gravitational potential energy, right? And the work here is due to friction, not due to the gravitational potential or gravitational force, right? So in this case, if our work is equal to negative 180 joules, and that should equal our change in energy, right? This is EF minus EI, right? So EI minus 180 should be equal to EF, right? So our initial energy was all potential, right? Our initial energy was all potential. So we started off with UGI, and there was no movement at the beginning, right? So even if we said K plus KI, well, there was no initial speed, right? Because they're at the top, there's potential to move, but there isn't movement yet. So Ki is equal to 0, and then that's equal to minus 180 joules, and then your final energy, right? That's going to be only kinetic and no potential at that point, right? Because once you reach the bottom of the slide here, you hit a height of 0, that arbitrary 0 point that we made, and so mgh, if h is 0, then your gravitational potential energy is 0. So for your final initial, or for your final energy, it would normally be UGF plus KF, right? And UGF is 0 because you're at that height 0, so it's just equal to KF. And KF we know is equal to half mvf squared, right? So if we want to figure out our final speed, right, at the bottom of the slide, that's what it would be. And so our initial gravitational potential energy was that mghi. This is subtracted by 180 joules, and then this is half mv f squared, right? So our mass was 27 kilograms. Gravity is 10 meters per second squared. Our initial height was 1.54 meters. This is all minus 180 joules. And then half times 27 kilograms, and then vf squared, right? And then we can solve for vf there. Right? So this here is going to give us our speed of the child at the bottom of the slide. So remember, the reason why we can actually use work here in this equation and still be able to calculate for the gravitational potential energy, there's this distinction that I failed to make at the beginning, which is the idea of work and using it in this type of equation here. The reason why we can use it is that this is work done by the friction force. It's not the work done by the gravitational force. So if we were to internalize gravity, which we are still technically doing because we're not looking at the work done by gravity, right? We're concerned now with the internalization of gravity. So we can calculate for the gravitational potential energy. But now we're concerned with work just due to friction force. So work in that case is still equal to the change in energy, and that's equal to the change in kinetic plus the change in gravitational potential energy. And like I said earlier, I wouldn't recommend even bothering with this stuff because you've already seen me mess up, and if I mess up, you guys more than likely are going to mess up too with this stuff. If it works for you, works for you. For some reason, I'm just tired or I'm stupid or a little bit of both. But I would just stick with work is equal to delta E. This is equal to EF minus EI. And then you can simply just look at, okay, what was my initial energy and what's my final energy? What components make up those energies, right? I started off only with gravitational potential energy. There was no movement at all. I only was sitting on top of that slide, right? I only have potential to move. At the final point, it's all kinetic, right? Because I've reached that bottom of the slide, right? And the height is 0. So it's all movement now. It's all kinetic. There's no potential energy. So that's why my EF there is only made up of kinetic. So your VF should then be equal to around 4.2 meters per second, I believe, once you calculate that out. Sound good for part D? Okay, cool. Now, final problem here. Problem 4. So this is gonna be horrible. Oh my gosh, I've had a rough night. So problem 4 is energy and work done by friction. So we have a 62 kilogram skier. So we have the mass of the skier is 62 kilograms. Is moving at 6.5 meters per second on a frictionless, horizontal, snow-covered plateau when she encounters a rough patch 4.2 meters long between points A and B. Coefficient of friction is 0.3, right? That distance right there for the friction for the rough patch is 4.2 meters, by the way. Okay. And they're moving at 6.5 meters per second, so there's an initial speed of 6.5 meters per second as well. So after crossing the rough patch and returning to friction-free snow, she skis down an icy, frictionless hill 2.5 meters high. All right. So part A is just asking what is the work done by friction on the rough patch, right? So work done by friction should just be equal to the frictional force, right? The kinetic friction there, times the distance traveled along that rough patch, right? Times cosine theta. Well, what is the frictional force equal to? How can we get that? They didn't give us a frictional force. Any ideas as to how we can get it? It is cosine 180 as well, yeah, because if you're moving to the right, friction would be acting directly in the opposite direction to the left. And so the angle there, so if this is your distance and your force is like this, friction, then the angle is 180 degrees, right? That's absolutely right. Yes, absolutely. And so what is that essentially? Remember, because for kinetic friction, remember we said it was mu times something specific, right? For kinetic friction, it's mu times, you're right, it's mg, but why is it mg? Because mg is gravity, right? But is it usually gravity? No, it's normal force. It's mu times Fn, normal force, right? And so normal force here is gravity, and you have normal force. Since there's no real net force along that y-axis, there's no movement along the y-axis, your Fg should be equal to Fn, at least for this horizontal point right here, right? So mu times Fn, and Fn would be equal to Fg in this case because there's no, at least for, like I said, at least for this here section, normal force is equal to gravity, right? Because there's no motion or no net force along that point. So mu Fn times the distance, right? That was 4.2 meters times cosine 180, right? So they gave us the mu was 0.3, and then normal force should just be mass times gravity, right? So mass was 62 kilograms times gravity, 10 meters per second squared, times the distance for that rough patch, and then this is -1 for cosine 80, right? So let me calculate this out real quick. 0.3. Go ahead. I don't know who had a question. Yeah, I'm saying like they're just moving horizontally though. There's no movement along the y-axis, right? So they're not sinking through the floor and they're not levitating, right? So that's why your Fn should be equal to your Fg. You see what I mean? But yeah, I got around, oh, actually, let me double check just to be sure. 0.3 times 62 times 10 times 4.2. I got around -781.2 joules. Yep, done the work. But yeah, that negative because of the cosine 180 there. So now part B is asking for how fast is a skier moving when she gets to point B. So once she gets to point B here, we want to figure out what the speed is at point B. And so if you encounter a rough patch, right, if there's a lot of friction, right, you're about to slow down, right? That's a logical way of thinking of it. And so we want to figure out, well, she was initially moving with 6.5. She's bound to slow down because of this friction surface, right, this rough patch. So how much did she slow down to? Or what was the final velocity that she slowed down to, right? So if we want to figure out, right, we know that there is work done, and that work done is going to equal a change in energy, right? And that change in energy is equal to EF minus EI, right? So work plus the initial energy is equal to the final energy, right? So for this, just to make things a little bit easier, right? Technically, if you want to think about it, there's a height here, right? So you have an initial, so this is, you have an initial gravitational potential energy, and then you obviously have initial kinetic, right? You're moving at a certain speed. You're moving that 6.5 meters per second. You have initial kinetic energy. And then you also have some final kinetic energy that we're trying to figure out, right? We're trying to figure out the final speed at point B. And you also have a final gravitational potential energy. What do you think these values are? Are they similar? Are they different? Are they the same? What's going on here with UGI and UGF from this point to this point? Yeah, they'd be same, right? Because you're still at that 2.5 meter height. You haven't changed your height at all. So if this was like 30 joules, theoretically, this was 30 joules, right? Well, then they just cancel out, right? So it doesn't even matter to factor in UGI and UGF. So we can actually technically just go ahead and erase them because they're at the same height. So you're just left with work plus initial kinetic energy is equal to your final kinetic energy, right? So if your work was negative 781.2 joules, plus your initial kinetic energy, so that's half times the skier's mass, which is 62 kilograms, times their initial speed, which was 6.5 meters per second, squared, and then their final, half times 62 kilograms times VF squared. Well, then you can just easily figure out the VF then. Right? Because we said that work is equal to the change in energy. That's equal to final minus initial energy. Work plus initial is equal to final. So our initial energy, we're at a specific height and we're moving. So there's kinetic and there's gravitational potential. The thing is, we know that due to this rough patch, there's going to be a change from the initial to the final kinetic energy. However, since you're here to here, you're still at that same height, your change in gravitational potential energy should be zero, right? Because you didn't change your height at all. So when you put initial energy and final energy, you're going to end up with the same value for gravitational potential energy on either side. So when you subtract one over to the other side, right? When you subtract it over, it'll be like if this was plus 30 joules and this was plus 30 joules, right? Then once you subtract one over, 30 minus 30, well, you get zero, right? So theoretically, like on this right-hand side, it should be like plus 30, for example, minus 30. Well, then that's zero, and you still get just this section here that we have to worry about, and that's directly affecting the speed. And so for final speed here, I think you should get around 4.1 meters per second or so. Somewhere around that. Sound good? Or you guys disagree on that one? I can double check here just to make sure. Good. All right. how fast is the skier moving in meters per second, which she gets to point C. So now from point B to point C, we have a change in kinetic and a change in potential, right? We can kind of think about this logically where, okay, if I'm going downhill, I'm probably going to be speeding up, right? So I should have maybe a faster speed at the bottom of this hill than I did at the top. At the same time, I changed my height, so there should be a decrease in gravitational potential energy and an equal increase in my kinetic, right? So if I decrease 20 joules of gravitational potential energy, I should see an increase of 20 for my kinetic, right? If I decrease 20 for gravitational potential, I should see an increase of 20 for kinetic. So if I want to figure out how fast the skier is moving, once again, well, I'm past that work, right? I'm past the idea of work here. I'm past this rough patch. I don't have to worry about work anymore. I just worry about how this change in height is going to change my gravitational potential energy and how's it going to change my kinetic energy, and then therefore how that's going to change my speed, right? So work is 0 in this case. There's nothing that's doing any work, right? We're not externalizing gravity, for example. There's no friction anymore, none of that. So this should just be equal to delta E, right? Energy is conserved in this case, so EF minus EI is equal to 0. So EF is equal to EI, right? So our final kinetic energy plus our initial, or plus our final gravitational potential energy should equal our initial kinetic energy plus our initial gravitational potential energy, right? Our final gravitational potential energy should be 0, right? Because if we make this our arbitrary 0 point, you hit a height of 0, mgh. If h is 0, then this part here goes to 0. So our final gravitational potential energy at that bottom of the hill should be 0. So we're just left with kf is equal to our initial kinetic energy plus our initial gravitational potential energy, right? So our initial kinetic energy was that half times 62 kilograms times vi squared, right? Well, what's vi here? What is vi? Because remember, we want to figure out point C, and we initially started out point B. So, excellent. Yep, it should be whatever your final was from here to point B. So our final at point B is 4.1. Our final for part B, for point B here, our final for point B is our initial when we're looking at the transition from B to C. So our initial here should be 4.1 meters per second, and then we square that, plus an initial gravitational potential energy, right? We had 62 kilograms times the acceleration due to gravity, and then times a height of 2.5 meters relative to this arbitrary 0 point. So this should be 2.5 meters there, right? And then that should be equal to half mvf squared, right? This is half times 62 kilograms and then times vf squared. And so then we can easily figure out what vf is once we solve this whole spiel here, right? And we should get around 8.2 meters per second or so, right? So roughly double the speed once you reach that bottom point, right? Makes sense, right? I mean, once you go downhill, you start speeding up. So there should be an increase in that kinetic energy, a decrease in your gravitational potential energy. Make sense for part C? Cool. Now, part D is kind of, either I messed something up for part A, or part A and part D are literally asking for the same thing. Because it kind of differs, though, with how you solve it. But part A and part D, I feel like they should be the same. But part D is basically asking how much mechanical energy was lost by the skier in crossing the rough patch, right? And so the mechanical energy that's lost would be equal to the thermal energy, basically. The thermal energy, right, would be like due to friction and stuff. So in this case, we can't really say that there's work, right? If we wanted to solve it by looking at mechanical energy and stuff like that. So we can't look at work there. So if we want to look at the thermal energy, right? So we will say work is 0. Energy was conserved, therefore, but that energy, right, that initial energy there at the top, well, that's made up of delta K plus delta U plus that thermal energy from the rough patch, right? That's assuming that there's a conservation of energy, and we just want to figure out, well, yes, there is energy lost due to that thermal energy right there from the rough patch, but we can account for it, essentially. That's the idea here. We can calculate it, we can account for it without necessarily externalizing work due to friction. So part A is like externalizing the frictional force. So we want to figure out how much work was done by friction. And then here is internalizing it, because they're asking about like mechanical energy, and mechanical energy is talking about like kinetic energy plus gravitational potential energy, and then plus any other energy sources that we have here. And so if they're looking at like energies lost, right? If they're looking at loss of energy, they're usually talking about a change in thermal energy that would cause a loss overall. Or at least it would detract from what's going on here. Oops. So in this case, our change in gravitational potential energy, once again, we said that was 0 because you're at the same height along this point from here to B, right? Along that rough patch, everywhere there, your gravitational potential energy should stay the same because you're not changing your height. So at that point, your EF minus EI, right? That's equal to 0. So EF is equal to EI. Our final should be all kinetic, right? There's no really, we don't have to factor in the gravitational potential energy since there wasn't a real change to it. And our actually, hold up. So actually, instead of doing that, how about I do this? Instead of doing EF minus EI, I'll say, yes, I'll keep the delta E this time, and I'll say that that's equal to 0, right? So delta K should equal negative change in thermal energy, right? So for delta K, I saw half mvf squared minus half mvi squared. There is a decrease in speed due to that rough patch, and that should be equal to negative thermal energy, negative the change of thermal energy, right? So half mvf squared, when we know that this is 62, and then the final speed was what? 4.1 meters per second, and we can square that, and this is 62 times 6.6.5 meters per second for that first part? For the initial velocity, or initial speed. So finding the change in kinetic energy here, right, there should be a decrease in kinetic energy because of that rough patch. It takes away from the system. And so then that should be equal to really what we got here. The work. Because the work due to that frictional patch, right, should be equal to the thermal energy. But if we go ahead and calculate it out, right, we can see half times 62 times 4.1 squared minus half times 62 times 6.5 squared. If you calculate that out, you'll see that you get like negative 780 joules or so. And then that's equal to negative change in thermal energy. And then you can see that the change in thermal energy is 780 joules, right? That's how much, that's the energy lost. That's how much mechanical energy was lost in that case. So I'm pretty sure that's what's going on here. But I feel like A and D are pretty much the same. I don't see a difference in what they're asking, except for the fact that here they're externalizing the force of friction. So they want you to figure out like what amount of work did friction do. And then here they're internalizing, where they're saying that, okay, we don't want to look at friction as an external force. We want to look at friction as being internal or a part of the system. And so when friction is internal, right, then we think of it as thermal energy. But yeah. Yeah, it's at 780.99, 781, 780, about the same. But you can see here that it's like almost pretty much the same as part A. So I don't know what exactly was the purpose of breaking this into two parts, unless I messed something up. Like with the last session, I'll look over parts A and D for this problem in particular, just to make sure that I didn't mess anything. And so, because I just don't understand why they would want you to do the same thing twice, basically. So I'll look it over again just to be sure, and I'll let you guys know if there are any mistakes. I'll communicate that via the GroupMe. But yeah, that's been the written homework. As you can see, like, I made a bunch of mistakes myself, so I'm nowhere near perfect. I try my best, but that just goes to show how this topic in particular is just ridiculous, and so it requires a lot of practice, and you just have to like be sure that you're on top of the math too, because there's a lot of signs, there's a lot of equations. There's like, I mean, the concept itself is not too bad. Like, you can understand why, for example, if you're going downhill, I decrease in my height, I decrease in my gravitational potential energy, and because of the law of conservation, right, of energy, well, whatever decrease in gravitational potential energy, I should see the same increase in kinetic, right? So the concepts aren't like horrible, like they're manageable, they're easy to understand to a certain extent, as compared to other concepts that we've done so far. Like torque, I know, is a little bit more difficult for people to wrap their heads around, but the concept of energy and the like conversions and stuff isn't bad for this chapter. It's just the math is ridiculous. Just the amount of stuff that you have to do, and the signs that you have to keep track of, and the points that you have to calculate. So going here to point B to point C, and then this problem required you to like look at what happens at the top of the loop, at the bottom, in the spring. You have to like break it up into so many parts, and it's just very, very tiring. So just like please do a lot of practice with this energy stuff in particular. Like torque, if you want to study torque the day of, I'd be happy to explain all of torque the day of the exam. Like torque is not horrible. The math for it isn't insane, but this stuff is where like it just like if I'm being honest, this is the one subject on the entire exam that threw me for a loop. So the only multiple choice questions I missed on the exam were about energy. The only written homework questions that I missed on the exam were about energy. So if that tells you anything, focus on energy is the most important part, because the delta stuff is, sometimes it'll be confusing, sometimes it'll make sense. When to use EI, EF, when to use work, when not to use work if you're internalizing versus externalizing. Hopefully I've cleared up some of that to a certain extent to the best of my abilities, but sometimes like just doing stuff in person helps a little bit more. So I'll definitely have my session on Wednesday from like, what is it, 10:15 to 12:15. So if you guys have De Jong section later in the day, I'm pretty much there available for you guys to ask any questions about this stuff before the exam or before the quiz. And then for those who are in Ansari section or De Nova section, who have different times for their lectures, also feel free to stop by whenever you have time, and I'll be happy to answer any questions about this stuff as best as I can. But for me personally, this is one of the more difficult topics for myself, just to wrap my head around, because it's just a lot of math, and so yeah, just a lot to keep track of, in addition to all the concepts that you have to understand to um, move through it. But anyway, that's enough talk. I need a drink of water. So, but yeah, I think that's it. I will stop the recording now, and hopefully you guys have a great rest of your night, and I'll see you soon.